Hello, everyone. Today we will have a math lesson that focuses on decimal numbers. Please concentrate and follow my line of thinking so we can understand these important ideas together. First, what is a decimal number? A decimal number is written in a place value system that uses 10 as the base. In this system, the position of each digit tells us a power of 10. That position is its place value. Let me give an example so it is clear. Look at the number 327. It is not just 3, 2, and 7 stuck together. We can break it apart like this. 3 times 10 squared, plus 2 times 10 to the first power, plus 7 times 10 to the 0 power. Now let us compute. 10 squared is 100, and 3 times 100 is 300. 10 to the first power is 10, and 2 times 10 is 20. 10 to the 0 power is 1, and 7 times 1 is 7. 300 plus 20 plus 7 is exactly 327. This shows that any whole number can be written as the sum of its digits, each multiplied by the matching power of 10. What about numbers smaller than 1? For example, 0.456. We can still use powers of 10, but now we use negative powers. 0.456 equals 4 times 10 to the negative first power, plus 5 times 10 to the negative second power, plus 6 times 10 to the negative third power. 10 to the negative first power is 0.1. 4 times that is 0.4. 10 to the negative second power is 0.01. 5 times that is 0.05. 10 to the negative third power is 0.001. 6 times that is 0.006. 0.4 plus 0.05 plus 0.006 equals 0.456. So we can describe any decimal number in a general way. From some negative power up to some positive power, we add up each digit multiplied by the corresponding power of 10. Each of those digits is one of the numbers from 0 through 9. This description is powerful. It tells us that whole numbers and fractional decimals share the same place value system based on powers of 10. Because a number's value depends on each digit's position, multiplying or dividing by a power of 10 does not change the digits themselves. What changes is the position of the decimal point. Each time we multiply by 10 or divide by 10, we raise or lower the place value by one level. Now let us see the movement in detail. First, multiplication. When a number is multiplied by 10 to the power n, the decimal point moves n places to the right. Multiplying by 10 to the power n makes every digit's place value n steps larger. Consider this example. 3.47 multiplied by 100 equals 347. Here's why. 3.47 equals 3 times 10 to the 0 power, plus 4 times 10 to the negative first power, plus 7 times 10 to the negative second power. Now multiply the whole thing by 100, which is 10 squared. We get 3 times 10 to the power 0 plus 2, which is 10 squared, giving 300, 4 times 10 to the power negative 1 plus 2, which is 10 to the first power, giving 40, 7 times 10 to the power negative 2 plus 2, which is 10 to the 0 power, giving 7. 300 plus 40 plus 7 is 347. So multiplying by 100 moves the decimal point 2 places to the right. Next, division. Dividing by 10 to the power n is the same as multiplying by 10 to the negative n. This moves the decimal point n places to the left, because each digit's place value becomes n steps smaller. Look at this example. 347 divided by 100 equals 3.47. 347 equals 3 times 10 squared, plus 4 times 10 to the first power, plus 7 times 10 to the 0 power. Dividing everything by 100 gives 3 times 10 to the power 2 minus 2, which is 10 to the 0 power, giving 3, 4 times 10 to the power 1 minus 2, which is 10 to the negative first power, giving 0.4, 7 times 10 to the power 0 minus 2, which is 10 to the negative second power, giving 0.07. 3 plus 0.4 plus 0.07 equals 3.47. So dividing by 100 moves the decimal point 2 places to the left. Please remember this rule. Multiplying by 10 to the power n moves the decimal point n places to the right. Dividing by 10 to the power n moves the decimal point n places to the left. We use this all the time. Next, let us see the relationship among fractions, mixed numbers, and decimals. Understand this well. There are 3 different ways to show the same value, and we can convert from one to another. First, turning a fraction into a decimal. Just divide the numerator by the denominator. For example, 3/4 means 3 divided by 4, which equals 0.75. Next, turning a decimal into a fraction. Look at how many digits appear after the decimal point. Write the denominator as 1 followed by that many zeros. Write the numerator as the whole number formed by the digits after the decimal point. Then reduce the fraction to simplest form. For example, 0.6 has 1 digit after the decimal point, so the denominator is 10 and the numerator is 6. That fraction is 6/10, which reduces to 3/5. Another example, 0.125 has 3 digits after the decimal point, so the denominator is 1000 and the numerator is 125. That is 125 over 1000. Divide numerator and denominator by 125, and you get 1/8. Now let us look at mixed numbers. A mixed number has a whole number part and a proper fraction part. To change a mixed number into an improper fraction, multiply the whole number part by the denominator, then add the original numerator. Keep the denominator the same. For example, 2 3/5 becomes 13/5. To change an improper fraction into a mixed number, divide the numerator by the denominator. The quotient is the whole number part. The remainder becomes the new numerator, and the denominator stays the same. For example, 17/4 becomes 4 1/4. Turning a mixed number into a decimal is also easy. First, change the fractional part into a decimal. Then add the whole number part. For example, 3 1/2 becomes 3.5. To turn a decimal into a mixed number, separate the whole part and the decimal part. Then convert the decimal part into a fraction. For example, 4.75 has a whole part of 4 and a decimal part of 0.75. 0.75 is 75 hundredths, which reduces to 3/4. So 4.75 equals 4 3/4. Be sure to practice these conversions. When comparing sizes, doing calculations, or simplifying expressions, choosing the form that fits the problem often makes the work easier. Now, let us talk about an interesting idea called repeating decimals. A repeating decimal has one digit or a block of digits that repeats forever after the decimal point. For example, 1/3 equals 0.3 repeating. Another example, 2/11 equals 0.18 repeating. Another, 5/6 equals 0.83 repeating, which means only the digit 3 repeats. Why does this repeating happen? When we convert a fraction, that is, one whole number divided by another, into a decimal, we use the long division process. During that division we keep bringing down zeros and continue. Here is the key idea. At each step, the remainder must be smaller than the divisor. For example, if the divisor is 7, then the remainder at any step can only be one of 7 possibilities: 0, 1, 2, 3, 4, 5, or 6. Now we begin the division. As long as the remainder is not 0, we must keep going. But there are only a limited number of possible remainders. This means that if we continue long enough, we will eventually see a remainder that has already appeared. Once the same remainder appears again, the entire process repeats from that point. Because the divisor and the remainder match a previous step, the next digit of the quotient and the next remainder will match as well. So the digits in the decimal begin to repeat, and they never stop. That is the root reason for repeating decimals. With only a limited set of possible remainders, repetition is unavoidable over infinitely many steps. Let me show a concrete example. Let us write 1/7 as a decimal. We divide 1 by 7. 7 does not go into 1, so we write 0 and a decimal point. The remainder is 1. We bring down a 0 to make 10. 10 divided by 7 gives a digit of 1. The remainder is 3. Bring down a 0 to make 30. 30 divided by 7 gives a digit of 4. The remainder is 2. Bring down a 0 to make 20. 20 divided by 7 gives a digit of 2. The remainder is 6. Bring down a 0 to make 60. 60 divided by 7 gives a digit of 8. The remainder is 4. Bring down a 0 to make 40. 40 divided by 7 gives a digit of 5. The remainder is 5. Bring down a 0 to make 50. 50 divided by 7 gives a digit of 7. The remainder is 1. Now look, the remainder is back to 1, the same as at the start. From this point on, the entire pattern repeats. 10 divided by 7 gives 1 with remainder 3. 30 divided by 7 gives 4 with remainder 2, and so on. Therefore, 1/7 equals 0.142857 repeating. So any fraction, when written as a decimal, is either a decimal with a finite number of digits or a decimal whose digits repeat forever. What decides whether it repeats? In the long division, if the remainder eventually becomes 0, the decimal ends. If the remainder never becomes 0, then because the set of possible remainders is limited, some remainder must repeat, and the decimal repeats forever. Class, we now understand how repeating decimals arise. Based on that, let us go a step deeper and state two very important conclusions. First, here is the core idea. Every rational number, that is, every number that can be written as a fraction, when expressed as a decimal, is either finite or repeating. It is impossible for a rational number to have a decimal expansion that is infinite and never repeats. Why? Because in long division, each step creates a remainder that must be smaller than the divisor. This means the set of possible remainders is finite. As we continue dividing, if the remainder is never 0, a previously seen remainder must eventually appear. Once it does, the decimal digits repeat from that point. If at some step the remainder is 0, the division ends, and the decimal has only finitely many digits. So a fraction written as a decimal must be one of these two types and only these two. Next, let us learn a very practical method to convert a repeating decimal back into a fraction. This method is clever. We use multiplication to move the repeating block to the left of the decimal point, and then we subtract to make the repeating part cancel. Let us try a common example, 0.6 repeating. We will name this number x. Because one digit repeats, we multiply this number by 10. 10 times x becomes 6.6 repeating. Now subtract the original x from 10x. On the left side, 10x minus x leaves 9x. On the right side, 6.6 repeating minus 0.6 repeating leaves just 6. So 9x equals 6 in words, which means x is 6 divided by 9. That reduces to 2/3. Therefore, 0.6 repeating equals 2/3. Now a slightly more complicated example, 0.47 repeating, meaning the two-digit block, 47, repeats forever. Again, name the number x. Because the repeating block has two digits, multiply by 100 to shift two places. 100 times x becomes 47.47 repeating. Subtract the original x from this. On the left we have 99x. On the right we have 47.47 repeating minus 0.47 repeating, which leaves 47. So 99x equals 47 in words, and x equals 47 divided by 99. 47 is a prime number, and 99 is not divisible by 47, so the fraction is already in simplest form. Therefore, 0.47 repeating equals 47 over 99. No matter whether the repeating block has one digit, two digits, or more, the core idea is the same. Multiply by an appropriate power of 10 to align the repeating parts. Then subtract to cancel the infinite repetition, and solve the simple fraction that remains. Please practice this method until it feels natural. Today, we learned the place value representation of decimal numbers, how multiplying and dividing by powers of 10 move the decimal point, how to convert among fractions, mixed numbers, and decimals, and why repeating decimals appear and how to turn them back into fractions. These ideas are foundational in mathematics. Please review carefully after class and keep practicing. That is the end of today's lesson.